All right. AP Physics 1 workbook, torque and rotation. Activity F, rotation. Now, in this particular scenario, this scenario is relating the classic example of a ladder leaning up against the wall. Now, normally speaking, okay, now, first of all, let's identify and sketch what the forces are, and then we're going to relate them more proportionally in just a second. Let's pretend this is a scenario that you are able to have enough friction for this ladder to stay put, okay? Because if you guys did your notes and you went through the video of the notes, I had an example like this with balanced torque, okay? The leaning ladder problem. But that one was a balanced torque problem. This one, the actual ladder is going to fall, okay? Read the scenario along with me. It tells us that a ladder is set against the wall so that the ladder makes a 30-degree angle with the floor. The wall is very smooth, but the floor is not. What does that mean? No friction where? No friction on the wall, but some friction on the floor, right? It says the ladder only remains motionless as long as a person holds it in place. When the person lets go, the ladder accelerates down and to the right. So what that means is if the ladder accelerates down and to the right, it's going to do this. I'm going to demonstrate it for you right now. Here's our leaning ladder. It rotates, doesn't it? Of course. Of course. See how it rotates as it falls? So it did not just accelerate down, it accelerated to the right as well. And as it does so, a convenient spot to take as the point of rotation would be that center of mass. You see that it is rotating about. So something to keep in mind as we go through this activity. Okay, it says Blake analyzes the scenario and identifies that 4 forces are acting on the ladder. Its weight, the normal force from the wall, the normal force from the floor, and the force of friction between the ladder and the floor. He then correctly ranks the magnitudes as gravity is greater than the normal force of the floor, which is greater than the normal force of the wall, which is greater than the friction force. Now, do you guys notice in that scenario, they told us that Blake correctly ranked them? That means he's right about that. Okay, so what we want to do is we want to now in part A, we want to, on the diagram above, label the forces that are exerted on the ladder. To clearly indicate the point on the ladder where each force is exerted, draw a force as a distinct arrow starting on and pointing away from the point at which the force is exerted. The lengths of the arrow should indicate the relative magnitudes, meaning what force should be the longest. I'm going to zoom in on this so you guys can see it. Shouldn't gravity be the longest? Okay, let's draw these. Go ahead and start with an arrow going straight down from the middle, and we're going to label that F sub G. Then we're going to have a force coming from the floor. What's that called? Normal force, but make it a little shorter. I'm going to call that, well, hold on. What did it tell us to label that one as? N sub F, right? And this, by the way, raises a good point. In class, we've been using normal force as a lowercase n, or we've been using F sub n, right? So if a prompt on an AP exam question tells you to use some other nomenclature, you need to make sure that you adhere to whatever that they tell you, okay? Be adaptable to doing that. Now, what other forces are acting on this thing? NW, so normal force from the wall. By the way, have you noticed? Gravity's longest, second longest is this, third longest, that means friction has to be the shortest arrow, huh? How do you draw friction? Which way is the ladder sliding at the bottom relative to the floor? Away from the wall, which means shouldn't friction be opposing that? Friction's going which way? To the left. And they had us label it kind of weird. They had it label as F sub F, but that's our friction force. Okay. Are you guys okay with the free body diagram for part A? Y'all okay with that? Yeah? Okay. Now, here is where part B, C, D, E are all going to be argumentation. Why is this greater than that? So now we need to put on our thinking caps, and we're going to relate this in terms of the different parts of the equation and how that relates to Newton's laws. Not only linear Newton's laws, but rotation as well. So explain why the force of gravity is greater than the force of the normal force on the floor. Okay, so which way is the ladder accelerating? Downward. So if the ladder is accelerating downward, that ought to be a lot to explain to you why the force of gravity is greater than the normal force from the floor. When the ladder is released, the center of mass accelerates downward. Therefore, if the center of mass is accelerating downward, what does that tell you? The downward force of gravity is greater than the upward normal force applied from the floor. Okay, now how about the next segment? Explain why the normal force from the floor exceeds the force due to friction. Okay, it says equations may be part of your answer, but equations alone are insufficient. Let me kind of leave you with this. What's the equation for friction? Friction is fun. Isn't the force due to friction equal to mu times the normal force? Yeah? And isn't mu always a decimal less than 1? Remember that? Okay, so what you're doing is you're taking, now this is not a sufficient enough explanation just to write an equation, right? What you do though is you use that as your pre-writing exercise, and you think to yourself, okay, well, how do I spell that out in a sentence? Well, how would you say it? Well, one reason span this out real quick. Go. One reason is that the force of friction is equal to the, what is mu? Coefficient of friction times the normal force. Since the coefficient of friction is always less than 1, friction will always be less than normal force. That's one reason. The second reason has to do with the torques that are applied, okay? So in order to see the second reason, let me go back to the picture. And let's zoom in on the picture here. And let's focus on the torques that are applied. Now remember, where are we rotating about? Are we rotating about the bottom, top, or middle? Middle, okay? Why are we rotating about the middle? Well, we already know the middle force is gravity. It's the greatest force. We're not comparing that to anything. We already know it's the greatest force. We are, in fact, though, comparing these two forces, right? And these two forces. So it doesn't make sense to rotate about the bottom or top, because do you guys know what happens? What is the torque equal to at the point of rotation? This was emphasized a lot in the videos. Hopefully you've watched the videos by now. Torque, guys, is equal to a perpendicular force times distance, right? Yeah? What is the torque at the point of rotation? At the point of rotation, see, the distance, d, is the lever distance. It's defined as where the force is applied to the point of rotation. So what about a force applied at the point of rotation? Zero torque. Let me put this in a visual sense. If you push a door open at the hinges, are you going to open it? No, because that's the point of rotation. What's going to provide you with the best amount of torque or the easiest amount of force? All the way at the other end. That's why doorknobs are all the way at the other end. Right? Not because it looks better that way. Less force needs to be applied. So torque, the forces need to be perpendicular to the lever. Here's the lever distance. The lever distance is from the point of rotation to the end and the point of rotation to the end. That's the lever distance in both cases. Now, do you notice how none of these three forces are perpendicular to that ladder? Here's what we need to do. We need to make a perpendicular force here. A perpendicular force here. This is the perpendicular force of perpendicular component of friction. And then finally, you need I'll do that one. You need a perpendicular component of normal force. Okay. Look to yourself, guys. What force is the greatest force? Remember, you're just comparing those two. Which perpendicular component is greater? Normal force is greater than that one, which means that the normal force is going to provide more torque to rotate this than will friction. Which makes sense, because isn't the whole thing rotating this way? Isn't it rotating? What does CCW stand for? Counterclockwise. The net rotation is counterclockwise. Okay, so there's more counterclockwise torque from the normal force related to clockwise torque from friction. Yes, there's also torque from this too, but we'll get to that in part E, I think it is. Okay, so let's address that right there. Let's address that right there. How do we state that in words? The second reason is that the ladder rotates how, guys? Counterclockwise. And by the way, if you want to avoid writing that big long word counterclockwise, here's what you do. And this is what you would do on an actual AP test too. You write it once, and then you put an abbreviation CCW. Do not assume that the reader understands that CCW means counterclockwise. Make sure that the reader knows because you have defined it as such. But once you have created an abbreviation, you're allowed to keep using that abbreviation, okay? But you have to signal the abbreviation first. Don't just assume the reader's going to understand what your abbreviation is right off the bat. Does that make sense? Okay. So the second reason is that the ladder rotates counterclockwise as it slides. So the CCW, the counterclockwise torque, provided by the normal force from the floor has to be greater than the clockwise CW. I'm going to define that one so we can use that later. Torque provided or created by friction. Okay, so we're using rotation as an example too to describe this. Part D, explain why the normal force of the wall is greater than the normal force or the friction force. Okay, go back to your picture. Why was this force, the normal force from the wall, greater than that leftward force of friction? What did it say here? The ladder accelerates how? Down and to the right. If the ladder is accelerating to the right, which force should be greater? The one that's pointing to the right. Isn't that the way net force works? Net force, an object accelerates in the direction of the net force. So the ladder accelerates to the right. Therefore, the rightward force NW, normal force from the wall, has to be greater than friction. You guys feeling okay with parts A, B, C, and D? You analyze it first, like I showed you how. You analyze it first, and then you take all that information and you summarize it in words, right? Which is what we're doing with the writing. Okay, last part. Here we go. Blake states that the ranking could not be completely determined until it was demonstrated that the normal force from the floor was greater than the normal force from the wall and friction combined. Explain how this expression is demonstrated by the scenario described. Well, we're kind of there. We're kind of there. Let's go back and take a look at it for a second. What we're really saying, oops. I didn't quite draw it proportionally enough for you to be able to see it, but what we're basically saying is that the torque provided by this force, what direction is this torque? No, direction. Isn't this force right here causing? I am still on text left hand. There we go. This force right here is providing a counterclockwise torque. Isn't this causing counterclockwise rotation? right? Just look at the meter stick. Watch it as it falls. As this thing, doesn't this end right here rotate that way? Yeah, that works. But then what is this force right here? What's that causing? Isn't that clockwise rotation? That's causing a clockwise torque. And then so is this. So if you look at this right here, that's causing a clockwise torque as well. So what we're saying is, in order for that statement to be correct, we already know that the ladder overall accelerates in the counterclockwise direction, right? Why is that possible? Because the counterclockwise torque here exceeds both clockwise torques. That's what's going on. Just have to summarize that in words. The force of friction, F sub little f. We don't need to write that. Just say the force of friction. The force of friction and the normal force from the wall both create clockwise torques. The counterclockwise torque from the normal force from the floor must be greater than the two clockwise torques because which way does the ladder rotate? At the end of the day, which way does it rotate? Counterclockwise, right? For the ladder to rotate counterclockwise.
AP Physics 1 Workbook, Unit 7, Torque and Rotation. Activity G, Rotation versus Translation. Remember to pause or rewind the video as necessary. Let's begin. Read the scenario along with me, please. Carlos brings identical yo-yos modeled as solid discs with rotational inertia I equals 1/2 mr squared to the top of stadium bleachers of height h. The yo-yos both have mass W or mass M and radius R and are wound so thin that the mass of the strings can be ignored. Carlos simultaneously drops one yo-yo while he lets the other unwind. Using representations, part A. Sketch a free body diagram for the dropped yo-yo and a force diagram for the unwinding yo-yo while they are in the air. Draw all relative lengths of all vectors to reflect relative magnitudes of all forces. For the free body diagram, each force must be represented by a distinct arrow on and pointing away from the dot. For the force diagram, each force must be represented by a distinct arrow positioned where the force is exerted. Well, the first thing I'm going to do, we're going to start with the free body diagram over on the right-hand side. And the first thing I'm going to do is I'm going to go ahead and draw the weight, the force due to gravity, right, is equal to mg. And I'm going to draw the exact same length for the unwinding yo-yo, because remember, they're identical yo-yos. Now, the free-falling yo-yo literally has only the force due to gravity, the weight. The unwinding yo-yo, however, also has a tension force going up from the edge of the yo-yo. Now, make sure to draw the tension force less than or shorter than the weight vector as you are accelerating, in both cases, in the downward direction. Okay, now, in the case of the first one, if we take a look at Newton's second law to be useful here, causing force minus opposing force equals ma. That means mg equals ma. And yeah, if you cancel the masses, a equals g. But I really want to look at the net force here. In the case of the unwinding yo-yo, mg minus tension equals ma. Now you'll notice you're subtracting from the weight. That means your overall net force is less. That means your acceleration has to be less. What that tells you is which yo-yo lands first? The free-falling yo-yo should land first. The dropped yo-yo, the free-falling yo-yo will land first. There is no upward force with the dropped yo-yo, so it is accelerating at a rate equal to g. The unwinding yo-yo has an upward tension force, so that the net force on the unwinding yo-yo is less. Therefore, it will have a smaller acceleration and thus take a longer time to travel the same distance. Part C, derive an expression for the time yo-yo 1, the dropped yo-yo, and the time for yo-yo 2, the unwinding yo-yo. I'm going to refer to these as time 1 and time 2. Let's find time 1 first. This is a free fall acceleration concept, so we can start with the idea that we have a free fall acceleration equation, a constant acceleration equation. Remember, free fall acceleration is constant acceleration. So y equals y naught plus v naught t plus 1/2 a t squared. Now, here's what we got to do with that. Y is going to be 0. Y naught is going to be h. V naught is 0, which means v naught t is 0. And you're going to substitute for positive a, because remember, a is equal to a negative g. So we got 0 equals the height minus 1/2 gt squared. We're going to go ahead and add this over to the left-hand side. And we have 1/2 gt squared equals the height. We will multiply both sides by 2, divide by g, and then square root. And the time would be the square root of 2h over g. Now for yo-yo 2, I mean, it is, the center of mass is free falling with constant acceleration. So at the end of the day, you still have to use y equals y naught plus v naught t plus 1/2 a t squared. And similarly, you're going to let y naught equal 0. You're going to let y equal 0. Y naught is the height you drop it from, which is the same as the height that the yo-yo 1 is falling from. V naught t is 0, and you have to replace positive a. Problem is, we don't know what a is yet. You got to find it. You just know it's going to be less than the acceleration in number 1, because we know yo-yo 2 takes longer to fall. So here's how we're going to do it. We're going to use rotational Newton's second law to find that upward tension. And you're going to use Newton's second law to find acceleration. Okay, so rotational Newton's second law, what is that? Well, that's net torque equals I alpha. Remember, net torque, the torque that causes rotation on a pulley, the force that causes a torque on a pulley, we're going to say essentially a yo-yo is a lot like a pulley or a disc rotating. So the force that causes that would be the tension, and the lever distance to the point of rotation would be the radius. So tension times radius is the torque, and that's going to equal to, we're going to substitute for I, and we're going to substitute for alpha. So I, if you recall, was 1/2 m r squared. And recall that A is equal to R times alpha. So if you solve for alpha, alpha is A over R. One factor of R cancels with one factor of R here, and the remaining factor of R cancels with the one on the left. And we are left with tension is equal to 1/2 ma. Using Newton's second law to find the acceleration, we're going to go causing force minus opposing force equals ma. So causing force is mg minus tension equals ma. You're going to be substituting this for tension. So 1/2, or mg minus 1/2 ma. Equals ma. We're going to add this over to the other side. And we get mg equals 1/2 plus 1/2 ma plus 1 ma is 3/2 ma. You'll see that the masses cancel, and when we multiply by 2 and divide by 3, we get that A is equal to 2/3 times G. Now, let's plug into this. 0 equals the height minus 1/2. And in place of A, we're going to put 2/3 G and then T squared. That cancels. And we get 0 equals the height minus 1/3 G T squared. Add this over to the left. We're going to multiply by 3, divide by G, and square root, and we get the time it takes for the unwinding yo-yo as the square root of 3 times H divided by G. You can clearly see it takes a lot more time, excuse me, it takes less time for yo-yo 1, therefore it's going to land first, than it does for yo-yo 2. Part D, each yo-yo lands on sticky tape and does not bounce upon landing. In a clear, coherent paragraph-length response, explain why yo-yo experiences a greater impulse due to the normal force from the ground. Well, impulse, if you recall, Impulse is equal to force times time, but it's also equal to a change in momentum. So, and momentum, if you recall, is equal to a change in mass times velocity. So the impulse was greater for the yo-yo that was dropped. Since both yo-yos come to rest upon impact, they both have a final momentum of 0. Impulse is the change in momentum, and since they both have the same final momentum, the one with the largest initial momentum has the greatest change in momentum. Okay, the dropped yo-yo has the largest initial momentum, right? Because it has the largest velocity. That'll lead to the greatest change momentum and thus the greatest impulse. AP Physics 1 Workbook, Unit 7, Torque and Rotation. Activity H, Rotational Kinetic Energy. Remember to pause or rewind the video as necessary. Read the scenario with me, please. A thin hoop of mass m and radius r is released from rest at the top of a ramp of length L, as shown to the right. The ramp makes an angle theta with respect to the horizontal table, which is fixed. The table is height h above the floor. Assume the hoop rolls without slipping down the ramp and across the table. Express all algebraic answers in terms of the quantities that are given and the fundamental constants. On the diagram below, draw and label the forces, not components, that act on the wheel as it rolls down the ramp, which is indicated by the dashed line, to clearly indicate at which point on the wheel the force is exerted. Each force must be a distinct arrow starting on and pointing away from the point at which the force is exerted. So just to be clear, ladies and gentlemen, we are drawing a force diagram on that hoop, not a free body diagram. Let's take a look. Well, first, you have the weight going down. Now, normally speaking, you would draw the components, right? Going this way, going that way. But you're not supposed to draw the components here. What you are going to draw is you are going to draw the normal force. The normal force, that much is going to be balanced. But you're going to move it right there. Okay, so before I do, let me erase some stuff here. Erase the components. There we go. There we go. Move that right there. So now they're proportionally drawn. Notice the normal force is drawn from the incline. The center of mass is drawn from the center of the hoop. Now, friction is always drawn less than normal force, so you're going to draw friction up the ramp and just make sure it is shorter than the normal force coming out of the plane. Part B, sketch an energy bar chart. Sketch an energy bar chart for a hoop Earth system from the time when it is at the top of the ramp to the time when it reaches the bottom. Well, here's the deal. Okay, let's go up to the top, up to the picture here, and let's talk about the energies involved here. Obviously, the title is rotational kinetic energy, but really what's going on here, guys, is conservation of energy, right? Why do we have this? Change in height, change in speed. So now let's examine our energies a little more carefully. So our initial energy is going to be, we have initial gravitational potential energy, mgh. Your translational kinetic energy initially is 0. And your rotational kinetic energy initially is also 0, because we're releasing it from rest. The final energies, well, you don't have any final potential energy, so that's going to be 0. You do have translational kinetic energy because the center of mass moves straight down the incline just like that. So your translational kinetic energy is 1/2 mv squared. And you're rotating as you're doing. So we have rotational kinetic energy of 1/2 I omega squared. Now, what's not too obvious at this point is how much translational kinetic energy do you have and how much rotational kinetic energy you have. So what I'm going to do is I'm going to draw the bar chart and we're going to come back to it. Okay. So I'm going to make up a certain number of units. And let's go, let's see, 1, 2, 3, 4, 5, 6, 7, 8, about 8 units high. And that would be our go. Just move that over a little bit. Okay, so that's our starting energy. Our starting energy is the gravitational potential energy. But I don't know the percentage of that energy that's going to be rotational and so what we propose is let's go ahead and actually set up part C first, which is deriving an expression for the center of mass of the hoop at the bottom of the incline. That's going to get us an idea of the kinetic energy that's rotational and the kinetic energy that's translational. Okay, you'll see in the derivation what the percentage is going to look like. And then we'll come back and complete the bar chart. So, part C. For the hoop consisting, or for the system consisting, excuse me, of the hoop and earth, there are no net forces that do work on the system. Therefore, the mechanical energy at the top will equal the mechanical energy at the bottom. E initial equals E final. Initial is at the top. Final is at the bottom. At the top of the ramp, there is only gravitational potential energy, while at the bottom of the ramp, there is both rotational and translational kinetic energy. So in other words, at the top, we have gravitational potential energy. At the bottom, we have translational plus rotational kinetic energy. Substituting for the types of energy, we get mgh equals 1/2 mv squared plus, and the rotational equation is 1/2 I omega squared. Now, the way to get a true view in terms of the percentage of how much that kinetic energy is translational and how much is rotational, put both of them in the same terms, meaning we're going to essentially substitute. We're going to end up substituting for I and omega squared so that we can write 1/2 I omega squared in terms of mass and velocity. And we're going to get a really good idea of how much percentage is translational and how much percentage is rotational. Since the hoop is rolling without slipping, we can substitute the value of v squared over r squared for the rotational speed squared, which is omega squared. How are we getting that? Recall that v is equal to r omega, which means if you square everything, v squared is equal to r squared omega squared. So if you solve for omega squared would be v squared over r squared. And you're going to substitute that for that. Let's make that substitution happen. We have mgh equals 1/2 mv squared plus, and we're also going to substitute for I too. Remember, we were told at the very beginning in the scenario that we have a hoop, okay? And the hoop has a rotational inertia of mr squared. So I have 1/2, and then in place of I, we're going to put mr squared. And in place of omega squared, we're going to put v squared over r squared. And you'll see the r squareds completely cancel. And so what are we left with? We're left with mgh equals 1/2 mv squared, that's the translational kinetic energy, plus, look what's left over here, 1/2 mv squared. That is the rotational kinetic energy. You can see you have equal amounts. Therefore, let's go back to our bar chart, and we can create a bar chart that is, if the potential energy was 8 units high, I made it arbitrarily 8 units high. Let's go ahead and make the rotational one 4 units high. Let's make the translational one 4 units high. Mass and radius cancel. You saw that, and then this mass is the same really as this mass and this mass, so mass cancels from everything. And we're left with GH equals, well, 1/2 mv squared, or 1/2 v squared plus 1/2 v squared is just, well, v squared. Next, what we're going to do is we're going to substitute for the height. The height of the ramp is equal to, if you go back and you look at the actual ramp itself, here's the ramp, here's the height. The height is the opposite side of L. So we could say that the height is equal to L times sine theta. So GL sine theta equals V squared. Finally, solve for V. square root both sides, and v is equal to the square root of GL sine theta. Part D, determine an expression for the distance from the edge of the table to where the hoop lands in terms of given variables and physical constants. So now we're talking projectile motion. Well, what do we remember about that? Well, this is the height. This is the distance. And distance, right, is equal to x, which is equal to v naught x times t. Now, v naught x is going to be the v we just found. It's the square root of GL times sine of theta. But we have to find also the time that it takes to fall. Well, we know the time it takes to fall. The time it takes to fall, height, is equal to 1/2 gt squared. Should probably be deriving it down here. So y is equal to y naught plus v naught yt minus 1/2 gt squared. Y on the floor is 0, y naught is the height, v naught yt is 0 because we horizontally launch it, and we have 0 is equal to the height minus 1/2 gt squared, which means the time is equal to the square root of 2 times h over g when you solve it for that. So d is equal to v naught x times t. Therefore, d is going to be equal to, the launch speed is going to be GL times sine theta, that was our answer for part C, times the square root of 2h over g. Now, when you have a square root times a square root, you can put it all together under one radical. So one radical would look like GL sine theta times 2h over g. Whoops, sorry, that should be an h, not an L. Okay, and what do we get? The g's end up canceling, right? So we get the square root of 2hl sine theta. Suppose the hoop is now replaced with a disc having the same mass and radius r. How does the distance from the edge of the table compared to where the disc lands in terms of your answer in part D? All right, so this is for a hoop, okay? And you can see the distance that you are away completely depends on the height of the table, which, by the way, is not going to change, not even for a disc. So that's not the big deal. The length of the ramp, which also is not going to change, and the angle is not going to change. So, I mean, if nothing's changing, then is it really going to be any different? I mean, isn't it going to be the same? Well, no, it's not. And the reason why is because a hoop has greater rotational inertia. A disc the rotational inertia is lower, which means there's less resistance to rotation, which means the velocity is going to be greater. The velocity is going to be greater at the edge of the at the bottom of the ramp and the edge of the table. So if distance equals velocity times time, and the velocity is greater and the time is the same because it's the same height, then should land farther, right? The disk has a smaller rotational inertia because more of its mass is closer to the center. Therefore, it is easier for the disk to begin to rotate. So, less of the gravitational potential energy will be turned into rotational kinetic energy, and more will be turned into translational kinetic energy. This means that the disk's translational speed at the bottom will be greater. Since it takes the same time to fall off the edge of the table, regardless of the launch speed, it will be moving faster off the edge of the table and will fall for the same amount of time. Therefore, it will land farther from the edge of the table. AP Physics 1 Workbook, Unit 7, Torque and Rotation. Activity I, Collisions. Please remember to pause or rewind the video as needed. Let's begin. The 4 cases above show 4 pucks, viewed from above, sliding to the right on a smooth table. Each puck collides with and sticks to a rod that can move or rotate with negligible friction. In all 4 cases, the pucks are identical and the rods are identical. The initial rightward velocities of the puck are identical, and the initial velocities of the pucks are perpendicular to the rod lengths. In cases A and D, the rods are fixed to the table by a pin with negligible friction. But in cases B and C, the rod is free to move. In cases A and C, the puck collides with the center of the rod. Okay, so we are told these things so we don't have to make any assumptions. Part A, for each case, determine whether angular momentum, linear momentum, and kinetic energy are constant. Put a check mark in the box if the quantity is constant, and if X in the box if the quantity changes during the collision. All right, let's kind of break this down for a second before we begin. In order for angular, back a second. In order for angular momentum to be constant, no external or net torque is acting on the system. In other words, what you have is you have maybe a change in rotational inertia causes a change in rotational speed, something to that effect, but you have no external torque being applied. When that happens, angular momentum stays the same before and after any collision. Linear momentum well, that's going to be constant. When I say constant, I mean conserved. When there is no external or net torques. Forces. Which means when 2 objects collide, so let's take, for instance, letter A. This is object 1, this is object 2. Object 1 is going to apply a force on an object 2, and object 2 is going to apply an equal opposite force on number 1. That's known as Newton's third law. Equal and opposite forces, right? Well, if there are no external forces, then momentum is conserved. If there is an external force acting on the system, then it is most likely doing some sort of work, and you have an external force, and linear momentum will be different, and you have what is called an impulse or a change in momentum. So let's examine each case one at a time. A. Now for A to have angular momentum, if you look, how can a linearly moving object like A have angular momentum? Well, it is possible, okay? But remember that to have angular momentum, a linearly moving object would have to be m times v. It has mass, it has velocity, but it has to have a radius away from the point of rotation. And when it collides, it's going to be at the point of rotation. So for case A, L initial is 0. There's no angular momentum before you collide. And when you collide, you stick to this, which means the speed comes to rest. And your final angular momentum, well, it's also 0. Linear momentum, P, is equal to mv. Okay? And you've got linear momentum beforehand, but speed comes to 0 afterwards, which means we have no linear momentum afterwards. Okay, so that's interesting. Here, linear momentum is conserved. Linear momentum is not conserved. Angular momentum is conserved. So angular momentum is 0 in each cases. The linear momentum, we have momentum before collision, but not after collision. So we can start filling this out by saying angular momentum is conserved, linear momentum is not. Now, clearly, if you have velocity beforehand and you don't afterwards, then kinetic energy can't be conserved either. So that one's an easy one. All right, let's take a look at case B. Case B, you have velocity beforehand, and the bar is free to move. Now, what is this thing going to look like when you actually hit it after collision? Well, after collision, the bar, because remember, the puck sticks to the bar. The puck is going to cause rotation like this, and so you're going to have the whole thing start to rotate. Like this. Partway through, it's going to be looking like this, and then partway through, it's going to be looking like this, and then partway through, it's going to be looking like this, and so on. And so you're actually, the center of mass, you can see the center of mass is moving in a straight line, but it's also revolving around the center of mass. So you have translational and rotational motion in case B. So, do we have linear momentum right before we collide here? Yes, we do. So linear momentum can be found, I keep saying linear momentum. Let's start with angular momentum. That's what I meant to say. Do we have angular momentum beforehand? Well, MVR. It's actually MVR perpendicular, if you remember. So that's the point of rotation for the bar. And if this is R, then, and this is theta, this is R perpendicular, which is half the length, right? And so do we have angular momentum beforehand? Yes, we do. Okay. Now, as soon as we continue, after we hit, do you have angular momentum afterwards? Yes, you do. Okay. Now, examine the situation. The puck applies a force on the bar, causing it to rotate. Is there anything else causing the bar to rotate? No, which means there are no external torques acting on the system. Therefore, angular momentum has to be conserved in the case B. Now, in the case of the collision, there's no net forces. Puck acts on bar, bar acts on force on the puck. So puck on bar, bar on puck. There's no external forces acting on it either. Therefore, we can say case B is conserving angular momentum. It's also conserving linear momentum. And the velocity is going to be less. When these two things stick together, you have more mass afterwards. More mass means less speed squared, in fact. So therefore, you have less kinetic energy when masses stick together than when they don't. So anytime you have an inelastic collision where masses stick together, you're not going to be conserving kinetic energy. So actually, it's fair to say that kinetic energy is not going to be conserved in, well, any of these cases. Okay, we'll get to that as we get to that. Case C. Well, again, you're going right for that center of rotation right there. So beforehand, your angular momentum is equal to 0. Okay, and again, why? Because it's MVR perpendicular. And R perpendicular is equal to 0, just like this is here. There's no radius from the point of rotation because you're colliding with the bar at the point of rotation. Similarly with KC, you're colliding with the bar at the point of rotation. There is no R perpendicular. So since that's 0, that is 0. Before and after collision, because once you collide with it, the whole bar and the whole puck and bar system is just going to move in a straight line like this, but only slower because it's more mass. So again, the angular momentum is conserved in a way because it's 0 before and 0 after. So it's a conserved value of 0, so to speak, just like case A. Now, the linear momentum, when the puck hits the puck and bar move together as one unit. The puck applies a force on the bar applies a force back on the puck. There are no external forces on the system. Therefore, linear momentum is conserved too. Kinetic energy is still not conserved because you're moving way too slow after collision. Case D. Remember, case D, the bar is pinned down and can only rotate. So what do we have here? Beforehand, you have angular momentum in terms of MVR perpendicular. Remember, there's R, there's theta, and then there's R perpendicular right there. You've got it. You've got R perpendicular. You've got a radius from the point of rotation. So with that said, you have angular momentum beforehand. When it sticks to it after collision, there's no net torque acting on the system. Nothing is causing the bar and puck system, because it's just all it's going to do is rotate about the pin. There's nothing that's going to cause it to speed up or slow down. No other torque causing it to do that. So angular momentum is constant. Now, angular momentum afterwards is going to be I omega in terms of an equation, but the amount of it stays the same because, again, no net torque acting on the system. Key idea. Linear momentum, on the other hand, you start with linear momentum beforehand. You start with P equals mv beforehand, and then afterwards you have nothing but angular momentum. You're not moving linearly anymore. Therefore, your linear momentum is done. And again, no kinetic energy acting on the system either. Rank the cases which had the most rightward linear momentum instantaneously after collision from the least rightward momentum to most rightward momentum. So the least rightward momentum, well, first of all, cases B and C have the most. So I'm going to start there. B and C have the most. Okay. Therefore, I'm going to put, remember, you're ranking from least to greatest, right? So I'm going to put B and C here at the end. They have the most, and they both have the same. Therefore, I'm going to set them equal. Now, what has the least? Well, case A has no linear momentum afterwards because you just stop. Case D has a decrease in momentum, okay, because the external force from the axis is not negligible compared to the internal interaction that transfers momentum out of the system by an impulse. So that would put D the lowest, right? And then A, and then BC. Okay, so let's actually qualify this with a descriptive answer justifying this. Since there are no external forces in B and C, and the systems in cases B and C do not lose any linear momentum, they have the same linear momentum as the ball initially. Now, case A has no linear momentum after the collision. Case D has some decrease of momentum of the rod puck system because the external force from the pin is not negligible compared to the internal interaction. The internal forces, between the puck and the bar colliding with each other, and transfers momentum out of the system by an impulse while the ball sticks to the rod and the system rotates about the pin. Part C, rank the cases in which has the most clockwise angular momentum taken about to the one that has the least. So from least clockwise to most clockwise angular momentum. Well, in case A and in case D, there are no external torques acting on the system. The force from the pin is exerted at the pivot, okay, which means the angular momentum before the collision in each case is equal to the angular momentum after, which means 0. So in cases A and C, the puck heads directly for the pivot, meaning the angular momentum of the system is 0 because there's no R perpendicular. Remember, MVR perpendicular, there's no R perpendicular, so there's no angular momentum before and after, right? So it's a 0 before, 0 after. In cases B and D, the angular momentum is the same since the puck is traveling the same speed at the same location relative to the center of the rod, before they collide. So how could we rank this? Well, you're still going to have B and D being the greatest, but your A and C are also equal too. Okay, they're just less. Therefore, we're going to rank them AP Physics 1 Workbook, Unit 7, Torque and Rotation. Activity J, Translation versus Rotation. Please remember to pause or rewind the video as needed. Let's begin. In this scenario, we have a cart of mass m that slides across a surface with negligible friction. The initial speed v, it encounters an incline of angle theta with the horizontal. At the same time, a wheel of mass m, radius r, rolls with a speed v, the same speed v, without slipping, and encounters the identical incline. Both the cart and the wheel reach the bottom of their respective inclines at the same time. The wheel does not slip as it rolls up the incline. Assume no energy is dissipated in the bearings on the cart. Part A. The forces acting on the cart as shown in the rectangle and the wheel, shown in the circle, are shown below, while both objects are on their respective inclines. The incline is shown as the dashed for reference. Part A1. Is the friction force acting on the wheel static or kinetic? Explain your reasoning. Well, the easy way to think about it, and we're talking about this right here. And by the way, if you're not sure why friction is pointing up the incline instead of down the incline, we'll explain that one next week in class. Okay, we need to use a new sign convention called the right-hand rule. Okay, we'll be learning that next week. But is that friction that's going up the plane for the wheel, is that static or kinetic? Well, let's think of it this way. The wheel is rolling without slipping. Okay, what that means is this friction actually causes the torque that causes the rolling. It doesn't reduce the mechanical energy of the wheel. Okay, only sliding friction would do that. Okay, for instance, if the wheel was skidding, like car tires with locked brakes, and you leave skid marks on the road, that's evidence of sliding, kinetic friction. But that's not the case here. Okay, so let's take a look. This is a case of static friction because the wheel is instantaneously at rest compared to the incline. What that basically means is there's a point of contact that the wheel is making with the ground every single moment it rotates. And static friction prevents that point of contact from slipping. That's why the wheel is rolling without slipping. And in fact, that same friction that's preventing the slipping is also causing the torque to keep the wheel rolling. Okay. Now, we're going to propose a verbal explanation as to why that friction force points up the incline. So explain why the friction force on the wheel points up the incline, even though this is not the direction opposite to the wheel's translational motion, because the wheel's translational motion, right, is going up the hill. And so we would think of the friction as being opposite to that. At least that would be the case. If this were a rough incline, which it's not. Remember, for the cart, it was a smooth incline. There was no friction. But if there were friction, okay, then velocity goes this way and the friction would be going down the hill, right? But that's not the case here, obviously, because it's a frictionless incline for the cart. However, you have friction going up the hill this case. Why? Well, let's propose an explanation as to why. Like I said, in class, I'm going to show you a shortcut technique called the right-hand rule that allows you to think about the direction of angular velocity, angular acceleration, and torque. And as soon as you figure out the direction of torque using the right-hand rule, you'll be able to figure out the direction of friction. So it takes a little bit of thinking, but it's actually very, very quick. Here's an explanation we can propose, however. If the wheel is to roll up the incline without slipping, its linear velocity and rotational velocity must slow at the same time. Okay, so what that means, let's back that up. So what's happening here? The linear velocity that's going up the hill and the omega, remember omega is the rotation that the wheel's experiencing, both of them are reducing because you're going uphill and you're losing speed, right? The friction force points up the ramp to provide a torque that opposes the change in rotational speed. That's what we're going to have to get a grip on with right-hand rule. That's what right-hand rule will help us with, okay? But the friction force points up the hill to provide a torque that opposes the rotational speed change as the translational speed changes. Also, another way to think about it is frictional torque opposes relative motion between the contacts. Without friction, the wheel would slide down the ramp. Static friction is opposing that motion going up the ramp. So that's another way to think about it too. But like I said, we do have another way of looking at this via a technique called the right hand rule, and we'll wait to put that together in class. Part B. Both the cart and the wheel will eventually momentarily come to rest at some point on their respective inclines. However, the wheel takes longer and travels a longer distance up its incline to momentarily come to rest than the cart does. Explain why this happens in terms of the forces in the force diagrams above. So if we're talking about a Newton's law explanation, well, if you look, the mass, remember the mass of the cart and the mass of the wheel are the same. It's mass m, which means if you have the same force due to gravity pointing down, that means you're going to have the same mg cosine going into the hill in both cases, which means the magnitude of the normal force should be identical for both. Now, what's different, obviously? Well, one, you have a friction force, and the other, you have mg sine theta. So we have mg sine theta, and here we have mg sine theta as well. So we have mg sine theta in both, but you can see the wheel has both mg sine theta going downhill and the static friction going uphill. So let's go ahead and tie all this together into a nice, easy explanation. Both the cart and the wheel have the same gravitational and normal forces exerted on them. However, the wheel has a frictional force that points in the direction of motion, so the total acceleration of the wheel is smaller than that of the cart. Okay, so that's the main reason. So since you have this frictional force, it's going to lower the acceleration because you have an opposing force. It's going to make the acceleration of the wheel smaller than the cart. So if the acceleration of the wheel is smaller than the cart, it means it takes more time for the wheel to slow down, and therefore it'll go a longer distance up the ramp. Explain why this happens in terms of conservation of energy principles. While both the cart and the wheel have the same speed and therefore the same translational kinetic energy at the bottom, the wheel is also rolling. This means it has rotational kinetic energy in addition to translational kinetic energy. Since the wheel has more mechanical energy at the bottom, it will have more potential energy and come to rest higher on the ramp. Therefore, it will be able to travel higher up the ramp. Because it travels higher up the ramp with the same initial speed, it must also, therefore, take more time to come to rest. Part C. While on the incline, not including friction, the cart and the wheel have identical forces F parallel acting on them directed down the incline. So F parallel would be mg sine theta. That's the F parallel they're talking about. If it were determined that the frictional force on the wheel is 75% of the strength of this F parallel and the cart travels distance L up the incline before coming to rest, how far does the wheel travel in terms of L momentarily? Well, I mean, think about it. If the frictional force is 75% of this, that means the net force is only going to be a quarter. Okay, the net force, let me write this a different way. The force on the wheel is going to be 1/4 of the force on the cart because, like I said, you're losing 75% of that to frictional. let's go ahead and describe this. The net force on the wheel is 1/4 as much as the net force on the cart. Again, this has to do with the fact that the wheel is losing 75% of the strength of the F parallel mg sine theta due to friction. Therefore, since the cart and the wheel have the same mass, the wheel's acceleration will be 1/4. So if the wheel's force is 1/4, then the acceleration of the wheel is 1/4 the acceleration of the cart. Using the equation v squared equals v naught squared plus 2ax, and since both the wheel and the cart have the same initial velocity and end with a final velocity of 0, then what that means is the wheel will travel 4 times farther up the ramp. Okay, why does that work? Again, solve for x. So x is equal to negative v naught squared over 2a. Okay, and a is the thing that I'm going to be subbing for here, all right? So the wheel, let's think this through. The wheel is 1/4 the cart. So if you're dividing by 1/4, you're multiplying by 4. So the wheel will go four times farther up the ramp.